So now we're going to look at epoxides, and we're going to start with section 14.7, which is nomenclature. So when you have a cyclic ether, it's when you have a ring that contains an oxygen atom. Now, as you can see here, there's a special parent name that is used to indicate the ring size. So we have oxiranes, which have 3-membered ring. We have an oxetane, which is a 4-membered ring. An oxolane, which is a 5-membered ring. And an oxane, which is a 6-membered ring. For now, we're going to focus our discussion on oxiranes. Oxiranes are also known as epoxides. Now, an oxirane can have up to 4 R groups attached to it. The simplest is ethylene oxide. Where all 4 R groups are hydrogen. Epoxides are common in nature. The 3-membered ring is a highly strained system. Similar to ethers, there are 2 methods for naming epoxides. In the first method, the oxygen atom is considered to be a substituent on the parent chain, and the exact location of the epoxide is identified with 2 numbers followed by the term epoxy. So if we look at the example in the book, okay, so we're going to identify the parent chain. And you're going to assign the parent chain so that the substituents have the lowest possible numbers. Okay, so this parent chain is a pentane. So we have 3 ethyl, 2 methyl, 2, 3 epoxy pentane. I want you to take note that the epoxy goes before the pentane. So this is not alphabetized with the other substituents. In the second method, the parent chain is the epoxide. So it would be an oxirane. And then everything else is treated as a substituent. So if we were to look at the example from above and name it, or the previous slide, and name it according to the second rule, 1, 2. Okay, this one is the one because they're ethyl substituents and they come first alphabetically over methyl. So it would be 1,1-diethyl 2,2-dimethyl oxirane. So let's practice that nomenclature. So here, according to the first rule, 1, 2, 3 would be the parent chain because this would give the lowest number to the substituents. So it would be 2-methyl, 1,2 epoxy propane. If we were to name this according to the second way, it would be 1,1-dimethyl oxirane. Now if we do one more, here, this is a cyclohexane. Okay, so it would be 1,2 epoxy cyclohexane. Let's move on to section 14.8 and look at the preparation of epoxides. We've already learned about how to prepare an epoxide from an alkene. So if you treat an alkene with a peracid, so this is a peracid, you get an epoxide. Now, typically the peroxy acid that is used, that we learned about last semester, is MCPBA. You can also use peroxyacetic acid. So this is meta-chloroperoxybenzoic acid. And the other acid that can be used is peroxyacetic acid. In lab, we are going to learn a green way to form an epoxide. And we are going to use cyclohexene as the alkene. When we use a peracid plus an alkene, the reaction is stereospecific. What this means is that if the substituents on the alkene are cis to each other, they will remain cis to each other. on the epoxide. So for example, here's our starting alkene. The R groups are cis, and the hydrogens are cis to each other. We treat this with our peracid. In our epoxide, the R groups remain cis to each other, and the hydrogens are cis to each other. And the same thing is true if the substituents are trans to each other. We can also prepare epoxides from halohydrins. If you recall, if we treated an alkene with Br2 in the presence of water, we would get what's called a halohydrin. Where we had an hydroxyl group and a halogen on adjacent carbons. This reaction is regiospecific, where the OH will add to the more substituted carbon. Of the alkene. We can take a halohydrin plus a strong base and make an epoxide. And I'll go through the mechanism on the next slide. So the mechanism is an intramolecular. Okay, we'll see these quite a bit this semester. Williamson ether synthesis. We form an alkoxide, and then the alkoxide functions as a nucleophile and the halogen leaves. So we have an intramolecular SN2 reaction. So if we look here at the mechanism, I have my halohydrin. I treat it with a strong base. The base is going to take a hydrogen. This makes an alkoxide. The oxygen can then attack the electrophilic carbon and the bromine leaves. And this results in the formation of an epoxide. The overall stereochemical outcome is similar to that of MCPBA with an alkene. So just remember that the stereochemistry is preserved. What this means is that cis groups will be cis to each other in the epoxide, and trans groups that were trans to each other will be trans in the epoxide. So now we have two methods for making epoxides. We can use a peracid and an alkene, or we can do a halohydrin and a base. So we need to add these reactions to our reaction roadmap. When we do these epoxide reactions, if we are making a chiral epoxide, then we will get a racemic mixture when we treat an alkene with MCPBA. Okay, so if the final epoxide is chiral, we'll have a racemic mixture if we use the alkene and peracid method. Now, if only one enantiomer is desired, we can use a chiral catalyst to select for one enantiomer. The catalyst was developed by Barry Sharpless. And we've seen this before when we looked at hydrogenation. Of alkenes. If the catalyst was chiral, we could favor one enantiomer over another. The reason for this is that if you look at the line in blue, there's no catalyst. And a catalyst can decrease the activation energy. And as a result, it can favor one enantiomer over another. The take-home message from this section is that if we use a chiral catalyst, we can lower the activation energy and favor one enantiomer over another. All right, now we're moving on to section 1410. And we're looking at ring opening reactions. Now, when you react an epoxide with a strong nucleophile, you can open the ring. let's take this example here where we have ethylene oxide. We treat it with NaOH. Now, OH minus can be a base or a nucleophile in the presence of water, and we can get a diol product. So let's take a look at the mechanism. So here, the OH minus is going to act as a nucleophile. Both of these carbons have a delta positive. The OH minus can attack, and the electrons go onto the oxygen. We have now opened the ring. Here are the two carbons of ethylene oxide. We have O minus. We have water. The O minus can take a hydrogen from water. And then we make our diol. When we learned about SN2 reactions, we learned that alkoxides make poor leaving groups. However, because of the ring strain in the epoxide, here it can function as a good leaving group. And I'll demonstrate this with an energy diagram from your text. So if you look at the blue curve on the energy diagram, here we have a hypothetical SN2 process where the substrate is the ether and the leaving group is an alkoxide ion. So you can see that there's a very high activation energy, okay, and the alkoxide is higher in energy than the ether, so that the delta H would be positive. It's endothermic. If we look at the curve in red, so you can see an epoxide is much higher in energy than the ether, and this is because it's less stable. When we use an epoxide, not only do we now decrease the activation energy, but now delta H is negative, and we have an exothermic reaction. So here we're using the strain of the epoxide in our favor. As a result, many strong nucleophiles can be used to open epoxides. In looking at these substitution reactions, we need to look at the regiochemistry and the stereochemistry. So first let's look at the regiochemistry. If the epoxide is unsymmetric, then you will have a nucleophilic attack at the least substituted carbon. This is a steric effect that you would expect from an SN2-like process. Two, when you have attack at a chiral center, then you have inversion of configuration. Again, something that you would expect from an SN2 like process. Right, the first example I want to look at is the following epoxide with this methyl substituent. And we're going to treat it with a Grignard reagent. And in the second step, we will add water. Now, I introduced Grignard reagents before as organometallics. We will look at Grignard reagents more extensively when we study carbonyl chemistry. But let's just look at the structure of this. Because we have the metal here, the metal has a partial positive charge. What happens is then the carbon that is attached to the magnesium will have a partial negative charge. So now we have a nucleophilic carbon. Right, so this carbon is going to attack a carbon with a partial positive charge. Okay, so Grignard reagents act as nucleophiles. Now they are water sensitive. We discussed them in the context of ethers. Right, they can be used in the presence of an ether. In the second step, we can add water to protonate the oxygen. If we were to add water, then we would destroy our if we were to add water in step 1, we would destroy our Grignard reagent. So let's look at the reaction. All right, we have our Grignard reagent. We are going to have attack on the less substituted carbon and open up the ring. Now, if you recall, we attacked the least substituted carbon. There is no reaction here. So the configuration stays the same. This carbon was not chiral, so there's no inversion to worry about. We now add water in our second step. Water takes the hydrogen. And we have our product. Now we're going to look at acid catalyzed ring opening. Okay, so here we have our ethylene oxide. We treat it with HX. And we have an alcohol and a halogen. So let's look at the mechanism of this reaction. Alright, so we have an acid And we can protonate the oxygen and make the carbons more electrophilic. Now X- can attack one of the carbons and open up the ring. Okay, so the difference here is we're going to first protonate the oxygen, whereas before we had direct nucleophilic attack and then we protonated the oxygen with water. Here the first step involves protonation. Okay, so the reaction can be taking place with HCl, HBr, or HI. In addition, if we have H plus in the presence of water, we can have ring opening, and there we'll get the diol again, because again the first step is protonation, and the second step is nucleophilic attack. So if we took our simple example of ethylene oxide, and now we had H plus in water, we would protonate. Now water can attack as a nucleophile, open the ring, we have an oxonium that we have to deprotonate, and we get our diol. We can also have H plus in the presence of an alcohol, and here our product will be an ether and an alcohol. Ether, alcohol. Mechanism, first step, we protonate. Now the alcohol can attack and open the epoxide. We can rapidly deprotonate, and we have our new product. If we look at the regiochemistry, it's a little bit different than when we opened an epoxide with a nucleophile. Okay, so here's our epoxide, and it's unsymmetric, and we treat it with acid. Again, it can be HX or it can be H plus in the presence of another nucleophile. Okay, so if we have a primary and a secondary, we will have attack at the primary position after protonation. If we have a primary and a tertiary, we will have attack at the tertiary after protonation. Okay. The reason for this is the electronic effect. And I'll go through this on the next slide. So we have our protonated epoxide. Now both of these carbons have partial positives. Now, they're not equivalent in their ability to support the partial positive charge. So when we're looking at a tertiary compared to a primary, tertiary can better stabilize the positive charge. So therefore, you'll have nucleophilic attack there. You can picture it like this. So that this is stabilizing more of the positive charge. So if we were to summarize, if we have a primary versus secondary, the dominant effect is going to be the steric effect, where you want to attack the least hindered position. If we have a primary versus tertiary, the dominant effect is the electronic effect, and we're going to have attack at the tertiary position. We need to remember this is only for the acid catalyzed case. Let's look at an example. We have the following epoxide. And we're going to treat it with H2SO4 and ethanol. First step is protonation, and I'll just draw that intermediate. Next step is ethanol attack. The ethanol is going to attack the tertiary carbon because the electronic effect dominates. Okay, so we have attack here, and the ring opens up. Our final product will look like this. So that is going to end our discussion of epoxides.